What I've done is I've drawn a couple of like sample shapes on these next two pages, and I've written the bounds of integration using Cartesian coordinates, and then we're gonna just change the bounds to our polar coordinates to kind of get a feeling for how those things change. So our first one is this semicircle above the x-axis with radius 1. And so the lower bound for y is 0. It goes up to the top of the semicircle, root 1 minus x squared. And then if we smush that down to the x-axis, we can see that x falls between minus 1 and 1. When we convert this into polar coordinates, we look at our region and we say, how close to the origin do I ever get? And the closest to the origin I ever get is 0. I'm thinking about my radius r. Closest to the origin I get is 0. And then I think about how far from the origin I get. That furthest distance is always radius 1. Doesn't matter at what point on the semicircle I'm looking at, that's how circles work. And then for theta, I think about kind of how close to the x-axis do I get. I start on the x-axis at some point, right here. Everything's on the x-axis. So my lowest bound for theta is 0. And then I think about how far I spin counterclockwise. And I go a full theta backwards there. So my upper bound for theta is pi. It might be helpful to like have a unit circle handy so that you know that going back 180 degrees is pi, going all the way around is 360, and all the different parts. So maybe review that if you're rusty on it. And then remember, our regular dA, dy, dx becomes r dr d theta. We can't forget that part. All right, next one is this full circle. And so my lower bound for y is I go down to the bottom of the circle, negative root 1 minus x squared. Upper bound is all the way to the top, but my bounds for x stay the same. And so my radius still has bounds that start at 0. The closest I ever get to the origin in the shaded region is on the origin. And I can go out a distance 1 on this radius 1 circle. That's the definition of a circle. And then again, the x-axis is in my shaded region, so the closest I ever get to it is theta 0. I don't have to spin anywhere. But then I go all the way around. So my upper bound for theta is a full 2 pi that it spins. Counterclockwise, 2 pi. And I have to remember to put my r in where my dr d theta are. Okay, so those two are integrals that we've set up in the past. This next one is a little bit different. So it's a semicircle with radius 1 and then a semicircle with radius 2. And so my lower bound for y is I start on that semicircle with radius 1, root 1 minus x squared, and I go up to the part that has radius 2, root 4 minus x squared. And then my x bounds, I just imagine projecting my whole surface down onto the x-axis, which tells me that I'm occupying between minus 2 to 2. So I'm going to convert this to my polar coordinates. Now my shaded in region is here. So the closest I ever get to the origin isn't 0 anymore. It's that first smaller radius, radius 1. And then the furthest I get from the origin is on that circle with radius 2. So now instead of going from 0 to the outside radius, I skip this first part. I start radius 1 away, and then I go as far as radius 2 away. But my bounds for theta are the same as we had in the first picture. I start on the positive x-axis, and then I spin back pi counterclockwise. Okay, these next two are a little bit tricky. So the first one is this triangle. that goes between the lines y equals minus x and y equal x, and then cuts off at the value x equals 5. So that's what I've written for my bounds of integration. Actually, I should undo that squiggle first, or else we won't be able to see anything. Okay. So, when I start at the origin and think about my shaded in region, I know that the closest I can possibly get to the origin and still be in my region is distance 0. So my lower bound for r is still 0. But I don't really know what this upper bound is, because kind of if I start at the origin and just start drawing out, my height changes depending on where I'm at. So that's kind of tricky. And what I need to remember is that x is equal to r cosine theta. But where I cut off right there was the upper bound x equals 5. So if x equals 5 and x equals r cosine theta, that furthest distance I get from the origin is that the radius r is 5 over cosine theta. And then my theta bounds are a little bit different here too. For all of our examples, we started on the x-axis, but here it's actually easier to start a little bit clockwise from the x-axis. So y equal minus x and y equal x both have 45-degree angles. So 45 degrees is pi over 4. So spinning down from the x-axis clockwise is rotating minus pi over 4, because we've always called going counterclockwise positive. So my lower bound for theta is minus pi over 4. And when I go as far counterclockwise as I possibly can, that's counterclockwise 45 degrees again. That's, did I just make that? Yeah. That's the angle pi over 4, so it just goes up to a positive pi over 4. R d theta. Okay, and let's do this last one. So it's again between the lines y equal minus x and y equal x, but now it cuts off at y equals 3. And so the bounds for this, I wrote x first goes from minus y up to y, and then y just goes from 0 up to 3. And we're going to do our r bounds first again. So my distance from the origin starts at 0 always, but then goes out to those different distances depending on where I am on the line. But I know that y is equal to r sine theta. My upper bound for y was 3, so 3 is equal to r sine theta. So that means that r is going up to the distance 3 over sine theta. That's what it means to be on the line, y equals 3. And then my thetas are starting here is the furthest or the least counterclockwise you ever are. And then out to the line y equal minus x is the furthest counterclockwise. And so now our lower bound is we've spun over that 45 degrees and we start at pi over 4. And then we spin counterclockwise, kind of another 90 degrees basically, to get up to 3 pi over 4. Yep, because here would be pi. So there's 45-degree gap in here. That's a pi over 4 gap. Pi minus pi over 4 is 3 pi over 4. I always mess up those angles, so I have to double check everything I do. Okay, so the takeaway here is that polar coordinates are easier for things that look circular. So these first few examples we did, everything was circular and our bounds were really simple. As soon as you start having hard edges, there's a chance that Cartesian coordinates are easier. So just always be careful and make sure you're picking the best way to solve a particular problem.